Hello YouTube viewers, welcome to my show Science Thursday. In today's episode, we're going to take a closer look at pole mounted substation or miniature substation. So let's dive right into it. Now, if you have been following my series, you must have understood that I've already covered substation. Then why do we need pole mounted substation? You have to understand, you don't live next to a substation. That's the biggest problem. Not everybody has like, okay, there's a substation next to me. Many of you may not even seen a substation close by, because they are generally built outside of the city. So since we are not living next to a substation, that creates a problem. How do we get efficient transmission of electricity next to you? Now, home voltage, basically the voltage that you are using, is not high enough, as in it is generally below 220 volts or 240 volts. Generally it's always below that. So in those sort of scenario, the problem becomes the ampere would be always high. Either they have to make very thick cable coming from your basically substation to your home, or they have to figure out a miniature substation. And you have to understand, when you have a neighborhood, basically multiple home, the current draw can be very high in terms of total watt consumption. You can have a scenario where you have half megawatt being consumed in a like small neighborhood. So in those sort of scenario, you have to have an efficient way of transmitting power from your big substations. Basically, you have these substations that are working on hundreds of kilovolt, and you want to figure out a way to deliver this safely. This is crucial aspect, deliver it safely to your consumer. So that is why we need miniature substation. Now, what is the solution of it? Solution is basically high voltage, or in terms of electricity, we call it medium voltage, generally 11,000 kV. Now, that's the maximum rate. In your country, it may be 9,000, in some other places, it may be 7,000, but generally it's upwards of 11 kV. Now, why 11 kV? Why not 33 kV? Why not 100 kV? You have to understand, air has a limitation. Basically, if you have two conductors that are exposed and they are carrying electricity, or let's say one is neutral and one is carrying electricity, there is a certain limit. Like, let's say the voltage on this conductor, live conductors, goes up, the electricity will simply jump. It will not care whether there is air gap or not. It will simply jump. To make sure that electricity cannot jump and randomly short out things, we have to create what we call air gap. So if you see the high voltage line, they're generally separate. So in 11 kV, you have to keep them, let's say, 1 feet apart. That's okay. But when you are talking about, let's say, 135 kV, you have to keep them, you have to make sure the nearest conductor where the electricity can jump must be bare minimum of 2 to 3 meters apart, or like 10 feet apart. So that's why you see giant poles carrying 100 plus kV. So that is infeasible for basically your neighborhood. So for neighborhood, 11 kV is like a good compromise. Basically, if the voltage is not so low that ampere would be too high, and it's safe enough, as in the air's dielectric strength, basically air's ability to stop the electricity jumping from one point to another, it's high enough. And you have to also understand, it also must take into consideration rain, because we cannot afford to put sheathing, basically insulation on these lines. It would be way too expensive. So with all that consideration, is the voltage basically high enough to reduce amperage? Is that voltage is manageable by air in a wet environment in a rainy situation? Yes, then we settle down on 11 kV. And it also means how high you have to keep it. You have to make sure, because if giant metal truck garbage truck starts to go below a conductor, electricity should not get excited and jump on it. So 11 kV has been chosen for that. And there are certain benefits of that. 11 kV is not too damn high, so the transformers that we need to step down that 11 kV to whatever you need, it's not that big nor expensive. So this is why we built this miniature substation that is on a pole. So that's the idea. You reduce the voltage as much as you can to make sure the air can handle it, your exposed conductor can handle it, your pole does not become ludicrously expensive. And then we created a small cheap transformers to run on it. So how the heck this works? Now, there are fancy ways to understand it, and there are simplified way. This is the simplified way. You have high voltage side, basically the thing that is generally on top. That's all you have to. Sometimes it can come through underground, but you will always see the conductors, basically whatever part that is carrying current will be spread out. Basically, they will always make sure that two high voltage conductors never come very close to each other. They will always make sure it's far apart. So that's the easiest way you can tell, oh, this is high voltage or low voltage. Low voltage could be this close, and high voltage will be always, they will make sure that it's far apart. So that's the high voltage side. That's the first, that's the incoming, that is coming from your nearest substation. Then it's taken care for safety. Now safety is generally done by multiple layers. So you can have what we call lightning arrestor. then you have safety taken care of, then after safety it goes to a transformer. Basically this is what is selling electricity to you. This is the final transformer before the electricity reaches to you. So understand, the electricity from a dam, from a coal-fired power plant, from a nuclear power plant, after many stages, like generally those transformers work on transformer, I'm saying those generators generally make very high voltage by default. They generally 2000 volt or 5000 volts by default, and then they go to another step up transformer where they go up to as high as 130 kV or sometimes 800 kV. Then they transfer to, you know, nearest substation. Then this is the last step down transformer. From this, it is a common thing. Basically here you can plug your mobile charger if you want to safely, you won't blow it up or yourself up. So this is the final distribution stage. So this is how it works. You have high voltage, you have basically safety mechanism, you have transformer, and you have distribution. How do you find out which is high voltage? Basically either would be on up, or whichever conductor that's carrying high voltage would be either very very spread out to make sure that it can not short circuit. So we handle safety on a very simple level. Basically, because we don't have infinite money, we generally first thing we do is put these puppies. These are what we call lightning arresters. So if lightning falls on your conductor, because it's a big giant metal object which will attract electricity, it routes it to ground. Basically it earths it safely to make sure that your electricity does not go offline, your transformer does not catch on fire. This is the first line of defense. However, you also have to understand, even though these are lightning arrestor, they also sometimes acts as a surge arrestor. So let's say in substation some fault occurred and they are opening the switch or closing the circuit breakers. Some of those time it also releases a very high voltage spike. This also acts as a double duty. Basically this can also act as a makeshift surge arrestor. And on top of that, then we come down to, like, this is the first line of defense. Then we come to fuse and isolator. Now isolator simply means you are pulling the plug. Now you have to understand, this is a combo unit. So in your substation these two will be completely different. You will have a fuse controlled by a circuit breaker and you will have isolator completely independent. Here we don't have the money, so we generally rely on this. Now if you see these rod, what they do is basically they explode. Now they explode internally. You will not see the explosion. You will hear the bang, but you will not see it. That's the whole idea. It's a hollow conductor, made sure to, not conductor I would say, hollow ceramic tube that can handle the blast, and it falls basically. And let's say somebody has to work on transformer but everything is okay. You see the ring, basically ring on that fuse, they will pull that down. This also acts as a basically isolator. This way they can safely de-energize the electricity. So this is pulling a combo duty. It's also allowing you to like deplug it, and it also acts as a fuse combo unit. And then you have to understand why the heck we put fuses on basically high voltage. Why we are putting fuses on like 11 kV line when we can buy fuse for 200 or 240 volts. So you have to understand, on these puppy basically, which is powering a transformer, the amperes are what affects the fuse. Now ampere rating you want to be keep low, otherwise your fuse will be very expensive. To basically compensate for that, we generally put it on high voltage side, and we figure out how to manage the voltage, because higher ampere is very hard to handle because it melts things. High voltage you have to just make sure it's far apart. So that's why we put high voltage fuses. That's why we are not going for high voltage, low voltage fuses, because even though those are cheap and you can buy it like in your local store, if you go there and ask like, hey, I want 600 ampere fuse, they will look at you like, what do you want? These fuses, they are barely rated for 10-20 ampere. So this is how we take care of the safety aspect. Now after the safety, we get down to the business, which is voltage transformer. Now the voltage transformer, you can have a single phase transformer, which will be generally 11 kV to 220 volt. Then you can have a three-phase something like this, which will do like 11 kV to 440 volt. Now do understand that 440 volt does not mean like each of the phase in the transformer is 440 volt. That simply means 220. But you can measure it. Basically, if let's say from phase A to from phase B, you can have a scenario where the voltage, basically the potential could be 440 volt, because one phase will be in positive, another would be in negative. So the gap between them is upwards of 440 volt. That's why these are rated at 400 volts. Three phase, you do understand that every phase is still 220 volt. So these are the two main types of transformer. Generally you will always see something like this, 11 kV to 440 volts. Now upward rating in terms of how much power it can carry, it's generally rated below 500 kVA. Now if you watch, there are generally steel plates etched onto the, sometimes etched onto, bolted onto, or like welded onto the transformer. You can easily read it. Now if you read it, you will always find it, they will always mention their load in terms of kVA, basically kilovolt ampere. Now you have to understand this kVA is upper limit. That means upwards of 500 kilowatt can be drawn from it. Now you might be wondering why the heck we don't simply say 500 kilowatt. It's a transformer, it's supposed to provide power. Why don't we say power that we understand? Oh, my motor is like 10 kilowatt, my motor is all that. The reason is power factor. Now, that's a completely complicated system, don't worry too much about it. Basically, if you have good power factor, closer to 1, awesome, you can draw upwards of 500 kilowatt. But if your power factor is bad, which generally it's bad, but let's say you are running computer have a bridge rectifier in your power supply, that messes up the power factor, so power factor becomes like 0.7, so that 0.7 gets multiplied. For that reason, you can never draw as much current as you want. Your practical current draw would be limited. That's why transformer always is rated in kVA. Now kVA at simplest conversion would be like theoretical maximum is 500 kilowatt. Now safe assumption is generally below 30%. You have to reduce it by 300%. Now if you are running in a big building or something like a colony, there would be people who invested a lot of what we call power factor correctors. These will correct that, and then they will allow in the same transformer they can get upwards of 500 kilowatt. So that's the rating aspect. Now you have to also understand, when you see these transformers, you will notice only 3 high voltage lines are coming. How the heck I'm getting 4 lines out of it? Like transformer is generally in all the schematics you see about transformer, 2 wire come in, 2 wire going out. How the heck we have a scenario where 3 wire comes in and 4 wire comes out? You have 3 high voltage line. How the heck you getting neutral? Now that is being accomplished by what we call delta Y connection. So delta is generally the primary. Basically this is where your high voltage is coming in. It's connected like a delta, so it only has 3 points. Now then how it's converted to, basically the step down side is generally what we call Y configuration. In Y you can see there are 4 points. So in the center point it acts as a neutral because the voltage there is 0. Now this neutral is shorted to the ground. Basically they put it to ground. The reason why it's there, because if you have neutral from your home, it's supposed to go here. It's not supposed to go to your ground. It's supposed to go here. This will cancel out the voltage. Any unbalance, it will cancel it out, and if there is any over voltage or any short circuit, then it will ground it. So this is how you get 3 input and 4 output. You have 3 high voltage coming in, and that's connected in like coils inside is connected in what we call delta configuration, and then you have Y configuration as the output, and the Y gives you 1 extra neutral conductor. So that's the aspect of the transformer. Now there are certain extra add-ons that you can see around. Sometimes you can see MCCB. Basically it's a bigger brother of MCB, miniature circuit breaker, but these are designed for very, very high amperage, because I already told you, if you want to go somewhere and ask them for 500 ampere fuse, it's very expensive. So generally MCCB, it's a newer development. It's not that it did not used to exist, it was very expensive, now it's cheap. So like this is a transformer near me. Basically you have a transformer and there is a big gray box that has this MCCB. Now on top, below that, once the output comes here, it is low voltage, this goes into distribution box. From this distribution box there is a metering also on that. The reason why we want to do meter here, this 2 reasons. First, if somebody steals electricity, the collection agency will find out, hey, my collection does not add up to how much electricity was spent here. Or let's say they figure out everybody is like, using electricity, paying the bill. That means there is electrical loss or short circuit somewhere along the line. For that reason, we also want to do monitoring here. And some advanced electrical grid also put smart equipments here, so which is basically allowing them to figure out the temperature, humidity, and all those other things that will help them manage the power situation very effectively. So these are the extra add-ons. These are not guaranteed that you're gonna find in the substation, and MCCB is kind of rare because it's a very new kind of investment. Distribution box, you may have a simple 3-line if it's going to a big basically community building. You will just have one 3-line system going. If you have like one transformer taking care of 5-6 homes, then you will say distribution box. Electric meter, again, it may be there, may not be there. So these are the extra add-ons that we add on to it. So this was my presentation on pole substations. I hope you liked it or learned from it. In that case, please leave the like and click the ad shown in this video. That will directly help me. If you didn't like it, don't worry about it. You can dislike it. Press the dislike button twice to show me your extra disappointment, and I would urge you to leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.